This is the solution video for problem set 8, problem 1. I've done a little pre-cooking on this problem just to speed things along because this first design part is actually fairly difficult, but the rest is pretty straightforward and pretty easy. So basically what I need to do is create a mod and counter for the multiplication circuit. And basically what I need to do, what I recommend, which I sadly saw almost no one do during the initial office hours, was draw a state diagram. Figure out what you're doing. Don't just blindly say, well, I need to take a counter, make it mod, and then add this other logic to it. That works sometimes. But sometimes stop and take a breath and do what you know how to do for designing a counter to begin with. And draw a state diagram. And in this case, we always want to use a more for counters because the output is a function of the state. It is the state in coding. And so that's what I decided to do. I've got my mod 3 counter for my 3 bits, 1 0 0 1 0 0. That's my counting sequence. And basically, what I know from here, if I start with this state, let's say I'm in the idle state. I'm waiting for I to become 1. As soon as I becomes 1, I want to load my counter with n minus 1, or I want to make this 2. This is regardless of what's going on. This is always going to take precedence. And shift is never going to be 1 during this, so I'm not going to draw that arrow. But if it's 0, when I'm just sitting in any one of these states, everything is 0, I want to maintain the value. I don't want to keep counting if shift isn't 1. That's what you see in every single one of these states. And then, basically anytime I get shift is 1, and I will never be 1 during those times, because this is the only time that shift is 1, and you see that I is 0. Then we can do 0, 1 will move us to here, 0, 1 will move us to here, and 0, 1 will move us to here. Now, because I and S are so completely independent of each other, I'm going to make one big recommendation, is that we kind of basically ignore I. And we're going to basically treat that as a parallel load. So regardless of what state we start in, if we get an I, we're going to load in 1, 0 into our flip-flops. So I'm going to make that suggestion first. But if you want to actually see how you could potentially do this using all this other nonsense mumbo-jumbo, you do this Q1 plus Q0 plus 0, 0. The IS is going to stay in 0, 0. This is 0, 0 with 0, 1. We're going to stay here, 1, 0, 0, 0, 0 with 1, 0. We're going to go to state 1, 0. In state 0, 1, we get a 0, 0, 0, 0. We're going to stay in state 0, 1. If we get a shift, we're going to decrement. We're in state 1, 0. We get a hold, basically 1, 0. We're going to decrement. And so this is going to go to 0, 1. So that's how you could do this, and you could just basically translate this into equations for D. So this would be your D. You can just implement this with D flip-flops. That's one possibility. Another possibility, if you really are paying attention to what's going on, and if you want to protect your circuit against making errors, the way I would do this is basically ignore I, take that out of the equation, and just make S. Basically, I'm just going to eliminate this row, so ignore this. And so what I'm going to do is I'm going to create my D flip-flop. I just need 2 of them. Yes, we normally do counters with T's, but D's are just so easy to do from next state tables. And so, what I'm going to do is I'm going to put a 2 to 1 multiplexer here with I. So this is a 2 to 1 mux. And this has got S0. It's going to have 0 and 1. And so when I is 1, I want to put in a 1. So this is Q1, and this is Q0. I've got my clock here. And I'm going to put a similar mux here. S0 gets I. And this gets a 0. regardless. So this is a 2 to 1 mux. And 1, 0. So now, pretty much, I just need to write an expression for this. And this is actually a complete truth table now. And so Q1 plus needs to is going to be 1 when we have 0, 0, 0. And we're going to have 2 don't cares down here. Sorry, my voice is very hoarse. So we can actually ignore this Q1 plus because that's not going to, we're ignoring this row. And so really, it doesn't really matter what we put in here. But we're going to put a 0 into there. So that way, this is always, every time we shift, we're going to output a 1. So this needs to be ANDed with, normally I would AND this with the shift, but that doesn't need to happen. And then here we've got Q0 plus is 1 with Q1, Q1 is 1, S is 0, Q1 is 0, S is 1. So this is just going to be the XOR, basically, of those two. No, I don't want to do that, not an XOR. So it's going to be I need to figure out how to draw this. So I'm going to put a OR gate into here, and I'm going to have 2 AND gates. So I'm going to have an AND gate here with S bar, Q1 bar, and Q0. And I'm going to have another AND gate here with S, Q1, and Q0 bar. And that basically makes my counter. And then moving on to 2B, basically I'm going to take Q1 and Q0 in, and basically I want it where these are both 0, which is only 1, which is basically just a NOR. So this is my Z. And now C is a register, C. And again, this is where I just recommend always do everything. Oh, sorry, this is a D, and I'm labeling this with C. Basically figure out when you're doing this. And so when C is 0, you want to maintain when C is 0 and load is C is 0, you want to keep the value of C. We're going to call this Q sub C in here. And so we're going to basically put a 4 to 1 mux, so it's got S1, S0, and we're going to put L and C. It really doesn't make a heck of a lot of difference. 0, 1, 2, 3. So when they're both 0, we want Q sub C to stay in. When L is 0 and C is 1, we want to clear. When L is 1 and C is 0, we want to put C out in. And so we get that from here. L is 1, C is 0, we put C out in. Anytime, and then finally, anytime C is 1, so we have C is 1, L is 1, we still want to clear C. So that's done.